Yes, good morning. I hope I'm audible enough. The essence of this training is to walk you through the process of imputing data for consolidation test. And the approach we are going to be taking in this training is to ensure that we start from the basis. Of course, we'll start by launching a source file that we'll use for our training. Then also we'll have a guide of a raw data that we'll be using in the course of the training. So I believe individuals should pick their notes to make jottings as the training proceeds. So we'll commence the training right away. So the first step is to launch my geosystem, which is the app that will be used to launch the source file we'll be working on. So let me open my geo system. That will take some time to open. Okay, good. So again, while I've opened my geo system, I also have to navigate from the geo system to the folder where the source file is saved. Because for this present project that I'll be working on, I've already opened it, and that's why you see that we have here list. Here is a list of projects that you recently opened, and this is the project we are concerned. I didn't mean we can't locate the project here, then we have to come here and say, click here to open a different project. Then from here, we can navigate to where the project is. So let's open the source file. That being done, we also have to launch uh, the raw data to see what we have so that we know what we are dealing with. And when you look at the source file, we have some basic information that is available to us. We have the borings, and we have for each boring, we have the borehole name BH1, BH2, BH3, BH4, BH5, and BH6. So each of these borings contains some informations. Like you can see, these are cards: card 1, card 2, card 3. And for each of those cards, they also carry some other information like the depth, pattern, description, and a series of test data that can be imputed. But for the purpose of this lecture, what we are interested in is the consolidation data. So we have to first understand which borrow we are dealing with and at which date. On that basis, we can begin to impute our test data. So let's find that out. So this is the sample sheet, and from here we see that we have borrow number slash depth. And for this particular training, the borrow number is BH5 and the depth is 27 meters. So I'll go back to my geo system and look for where I have BH5 here, which is here. Then from here, I have my depth. This is 0 meter, 2 meter, 25.5 meters. So I have to find 27 meter. Usually, when we are imputing lab data, any lab data being imputed will always be after the end of hole. So which means if I'm looking for a particular depth, it will be at the end of hole. I'll start searching from the end of hole. So in case the data does not exist, then I have to create a card for that particular depth I'm interested in. But let's find out, do we have 27 meters? Okay, so great. These are our 27 meters. And you see the list of tests we have here. We have Atibag, CBR, grain size, quick test, moisture contenders, proctor, share test. These are descriptions. Then we have consolidation. So this is what we are interested in. So we'll come to the consolidation data. So now that we are at this stage of the reporting, we have to input our data. Like you can see, we have the material description. So to get the material description at 27 meters, you have to click on the list of material, and the way it is being arranged, you can see these are the depths 0 to, we have 0 meter here, 2 meter here, 25 meter, 33 meter, 39 meter. And you quite notice if you want to place where 27 falls into 27 falls into 25.5 and 37 meters. So the description that precedes, should in case the depth does not exist, the description that precedes that particular depth will be used for a non-existing depth in the description. So for 27 meters, we'll take the description of 25.5, which is gray, fine to medium grain, clay sand. So you click on it. Also, you also have to note, you notice that your cursor is blinking here, so you have to backspace it, or else by the time you are generating your final report, you might not have this description showing. Then another information is the sample date. You can always get your sample date from your assignment sheet. Uh, I don't have the printed assignment sheet here, but I have the soft copy of the assignment sheet, so I can come here. I can see this is my BHO5, this is 27 meters, and this is my sample date, which is 4/07/2025. Then I come here, I type 04/07/25. The information about the liquid limit, if it is done, will be imputed here automatically. Same for the plastic limit. Then the USCS sign will also be imputed or can be done manually. What we are also concerned with is our final density. And to calculate our final density, uh, the formula for density is density is equals to mass mass divided by volume. Remember, our volume is equals to area times height, while our area is equals to pi times radius square. So in this case, what's our diameter? Our diameter is equals to 6 centimeter. Our area, our height rather, our height is equals to 2 centimeter. Definitely, our radius is equals to diameter divided by 2. So our radius will be equals to 6 divided by 2, and that will give us 3 centimeter. Hence, our area now will be equals to uh, 3.14, which is our pi, times 3 raised to power 2. So that's our area. So by the time we do the arithmetic, we find out that our area will give us 28.27 uh, centimeter square, while our volume will give us 28.27 times 2. And by the time we do the multiplication, we are going to be having 56.54, which is approximately equals to 56.55 centimeter cube. So that's our area. Then with that, we can easily calculate our final density, uh, which is equals to uh, our final density will be equals to uh, will be equals to sorry moist mass of specimen after test divided by volume. And by the time we come and check our data, uh, this will be our moist mass of specimen after test. As you can see, moist mass of specimen after test, which is 83.65. So, which means that will give us final density is equals to 83.65 divided by 83.65 divided by 56.5 56.55. By the time we do the derivation, let's find out what we are going to get. 83.65 divided by 56.55, and that will give us that's going to give us 1.479 grams per centimeter cube. So hence we can come back to our data entry. We know that our final density now is 1.579. Then we'll run the test. From our raw data. We'll also get the information. That's why we have here tested by. So the information should be imputed here. But I know we have CO, COCA, check by IO, I2, we have ENG. Then the next one is to come here with, and you can see here we have initial sample measurement. That means the sample that was taken before the commencement of the test, that is before the test was being run. And here we have wet weight plus star. By the time you come here, we also have moisture mass of specimen before test. So which means the mass that was taken before the test was done, and which is the same as what we have here, initial measurement and the wet weight. So wet weight in most cases is also the same thing as moist mass. So what we have there is 96.31. Our tar, our the next one is dry weight plus tar, and we can see here weight of dry soil only. So by the time we come here, we have 63.04. Then our tar will be 0. So after that, we come here, the height of our sample, just like I said earlier, is 2, the diameter is 6. Then the weight here is equivalent to the weight we have in here, which is 96.31. Then our specific gravity is also another information that will be provided from other lab tests that has been done. I can check what the specific gravity is from the provided document at BH5 27 meter. I can see that my specific gravity is 2.29. So by the time I come back to my data, I can impute that here 2.29. Then once I'm done with that, the other thing that needs to be done is to calculate our overburden pressure. How do we get our overburden pressure? Uh, just a minute so that we can see both sides. So overburden pressure is equals to unit weight of sample before test times gravity times sorry times height of sample, and unit weight of sample before test is equals to density of sample before test times gravity due to acceleration. So let's find that out. What our units? So simply I will just call this unit weight is equals to what was our density before test. So we are going to use this mass. Remember, our density is mass divided by volume. But since we are interested in the mass before the test, so we are going to say that's 96.31 divided by the volume, which is what we've calculated initially, which is 56.55. Let me open a bracket here. Uh, Times 9.81, which is our gravity due to acceleration. So what's our unit weight? Unit weight is equals to, let's bring out the calculator. We have 96.31 divided by 56.55 times 9.81. So that will give us 16. That will give us 16.70 kilo kilonewton per meter cube. From there, we can calculate our overburden pressure, which will be equals to 16.70. Remember, the height of interest in this case is 27 meters. Sorry, this is not height of sample. This should be depth of sample. That was the depth at which the sample was taken. So the depth at which the sample was taken is 27 meters. So that's 16.771 approximately times the depth, which is 27 meters. By the time we do the multiplication, I said times 27, I will get 451.0.10 kilonewton per meter square, or kilopascals the case may be. So from there, uh, I know what my overburden pressure is. My overburden pressure is at that depth is 451.10. My as tested height is 2. Tested diameter is 6. Then post test moisture content. That's the moisture content after the test has been done. And we also have the wet weight plus star. And if you look at what we have here, we have moist mass of specimen after test. So that's what we have here. That's 83.65. Our dry weight still remain the same as what we have here. That's 63.54. Then our tar remains 0. So with that, we've completed the first phase of our data input. As you see, we have two stages. the sample and test info, and the and charts, reading and charts. So here we can now start to impute values. And by the time you look at this interface, this is where we have our graph being plotted, which is the graph uh, of deformation against uh, pressure. We have the graph of deformation against pressure. We also have the time rate graph down below, which will reflect. And you see, this is where you enter your data from. Pressure, you enter your pressure here, then you have your elapsed time and your reading. So for each pressure, we have elapsed time and reading, and you can see different pressures here. We have 12.5, 25, 50, 100, 200, 400, 800, which is the loading pressure. Then we also have the unloading pressure, 200, 150. And we have our elapsed time here, and this is our dial reading. So which means if we are going to start, before we start, let me just quickly explain some other things for us to note. By the time you look at here, our curve can either be in form of strain against pressure, or we can say we want it as deformation against pressure or void against pressure. So with that, if you look at the dial reading here, you see that is in mm, but in the software we are using, the dial reading is in cm. So one thing that we need to note, which is a little bit the technical part of it, is to ensure that we convert our dial reading from mm to cm, and the conversion factor from mm to cm is to divide the value we have in by 10. So which means 1 is equals to 10, sorry, 10 mm is equals to 1 cm. So which means for our first value here, we have 6, so we have to divide it by 10, which means whatever we are having should give us 0.6. The next one should give us 0.5918. So those are the way the value should be when we are putting it into the software. How to achieve that also in the software is to also look at what we have here, which are the divisor. We call it dial divisor, which is a quick way to convert. It depends on what you are trying to achieve and what you have. Like here, I can see a divisor of 1,000, a divisor of 10,000, and a divisor of 100,000. So let's say I want to start with the first pressure that I have here, which is 12.5, and impute my pressure at 12.5. Then my first elapsed time is 0, and the die value for the last time. I can decide to say I want my divisor to be 1. Then if my divisor is 1, it means that I'm imputing my values directly. So instead of putting 6 as the first value, I will have to type in 0.6. If I'm choosing my divisor to be 1000, then my value here becomes 6,000. Sorry, becomes 600. That will give me 0.6. If I'm taking my divisor to be 10,000, then my value becomes 6,000, as the case may be. And usually, by the time you look at most of our templates, especially depending on the die gauge that is in between the range of 9 downwards, we always write our data to 3 decimal places, just as you've seen here. You can see. So usually the logic is to make your divisor 10,000 when you have it like this. Then when you have it like that and you make your divisor 10,000, then you can just assume the decimal point is not there, then you write the whole figure you have seen. So I can come here and say 6,000. My next time elapsed is 0.1, then the die reading will be 5.91, sorry, 5.18 rather, 5.918, then the next one 0.25. Uh, you see, so here should be 5918 at 0.25. I will have 5912, 0.5, 5906, 1, 5898 at 2. I have 5888 at 4. I have 5872 at 8. 5860 at 15. I have 5844 at 30. I have 5818 at 60. 5788 at 120. I have 5756 at 240. I have 5732 at 480. I have 5718 at 1140. I have 5704. So usually by the time I reach the end of uh, my die reading for a particular pressure, you see that it takes me to this next stage. I press enter again, then it takes me to another data sheet for the next die reading. So for my next die reading is 25. I press enter again, then if you notice, it has already imputed a value for me at 0, which is the last value of the die reading that was taken previously. So you don't have to enter anything here, you just have to go straight to the next data on your data sheet, and you have 0.1. We have 5660, 0.25, 5656, 0.5. We have 5648, 0.1. Sorry, that was 1. So as you can see, we've been able to impute the pressure, the elapsed time, and the die reading for each of those pressure at 25, 50, 100, 200, 400, 800. And you see that immediately after the 800, we have the unloading, which starts with 200. Then you notice that there are no data in between until we get to a last time of 1440. So we have 1440, then the data is 640. Uh, then we go to the next elapsed reading, which is at 100. We have 1440 again, that's 856. So as you can see, we have uh, our graph here, and just like I said, we can decide to say the form in which our data should be imputed. It could be as deformation, it could be as void ratio. Let me increase the volume. So we have void ratio here, and we have our pressure here. As you can see, void ratio. You can see applied pressure. And we can also have it as percentage strain, and we have applied pressure as well. So let's adjust this a little bit. Uh, just to make sure it captures the lines, so I can, uh, as you can see, so this is fairly okay and should give us a better result. So at the end of the day, we can come to our reporting and see generally what we have. And as you can see, the data we've imputed, we have our overboarding pressure, blah blah blah. We see that everything is intact. Then we come here, save. Then we can close and go and do the next one. Well, I hope with this, we've been able to capture the whole process of data entry for consolidation data. If there's any question, you can always refer back to me. via WhatsApp chat or via email. Thank you.